Then let's see the routing and the forwarding. I bet for this slides you guys are very familiar about it because we already talked about this slides in the previous lectures for twice. So let's quickly go through it. For the routing algorithms, it will determine the end-to-end path through the network and then generate the forwarding table. For the forwarding table will determine the local forwarding at this router. Then, since we are dealing with the routing algorithms, so usually the solution we analyze the routing algorithm is based on the graph structure, data structure. For example, this one, the graph G include two set N and set E. N is a set of routers. For example, here the U, V, W, X, Y, and Z. Each one represent a router. And for set E is a set of links. For example, UV, UX, VX, etc. And all these pairs represent a link between two routers. And for each link is a direct connected link for each two routers. And also the graph abstraction can be also used for other network contexts. For example, the P2P architecture, when we do the analysis, we can also use a graph abstraction for the P2P architecture. And for that, for P2P architecture, the N is a set of peers and the E is a set of TCP connections. Another very important factors for the graph abstraction is the cost. The representation for the cost could be this format with a lowercase c parentheses. Within the parentheses, we have two router names, x, for this one, the x and x prime, which represent the cost of a link x to x prime. For example, CWZ equal to 5, which represent the link cost between W and Z, the cost equal to 5. And also the cost can be set as O equal to 1. And that's a one type of cost assignment. Another type is we just assign the bandwidth for the link as a cost for each link, or we give the congestion status for each link treated as a link cost. So in order to calculate the cost for the path, actually the solution is very simple. It's quite straightforward. We just add each link along the path together. We add them together. We can get the cost of the path. Then we have a key question. So what is the least cost path between U and Z, or between V and Y, whatever pairs you ask? So what's the least cost for that path? Actually, the answer is based on the routing algorithm. That's the reason why we need a routing algorithm, because it can help us to find the least cost path between each pair of routers. And the routing algorithms can be classified into different categories. So first, let's see the category is based on the required information. We can divide it into two types. The first type is the routing algorithm is require the global information, which means all routers have a complete topology of the entire network and also the link cost information. For example, the link state algorithm is based on the global information. Another type is a decentralized algorithm. The router knows the physically connected neighbors and the link across the two neighbors. So that means each router only know the directly connected neighbors or routers, and also know the directly connected link cost. Only know this local information. And also each router, they will continually or periodically to send the information to its neighbors to notice its neighbors what my status right now. So they will exchange the information with their neighbors. For example, the distance vector algorithm will depends on the local information. And for the other category is based on the route status. We can divide it into static and dynamic. For the static one, the routes change slowly over time. And for this static one, must with the human interaction, the forwarding table can be changed. Otherwise, the forwarding table will keep the same. And the other type is a dynamic one. The routes will change more quickly, periodic update, or in response to link cost change. So when some events happened, the forwarding table will be changed. It's based on that event. So it's dynamically and automatically updated for the forwarding table under the dynamic type. Then first let's see um, the routing algorithm rely on the global information. We call it the link state routing algorithm. This routing algorithm actually is based on the classical algorithm. Name is the Dijkstrata algorithm. For this one, rely on the global information. Therefore, each routers must have the entire network topology and also link cost for all other nodes or for all other routers. And for this global informations, they will share through the link state broadcast way to notice all other routers inside this topology. And all nodes have the same information. Otherwise, we cannot call it global information, right? Computes the least cost path from one node, which for this one node we call it source node, to all other nodes. Then we give the forwarding table for the source node. And for the iterative, after k iterations, know least cost path to k destinations. So that means for each iteration, it will know one destination's least cost path. Then let's learn some notations. I'm sorry, notations. For the first one, the cost x y, which is a link cost from node x to y. If there's no direct link between x and y, we will give the cost equal to infinity. For the dv, it's the current value of a cost of path from source to destination v. This is the cost for the path and not for a link. This one is for a link. This one is for a path. PV is a predecessor node along path from source to V. I can give you an example. Suppose the source node is U and along the path is a U, W, X, Y, and V. This is the path. So the PV will be this one, which is the predecessors of V, which is router Y. And for set n prime is a set of nodes whose least cost path definitely known. And for this slides show us the pseudocode for the Dijkstrata algorithm. it will include two steps. The first step, it will do initialization, and then we'll go into the loop. So for the first initialization step, it will initially it will add the source node into this n-prime set. For all nodes if v adjacent to u, then we will set this link cost or path cost, I'm sorry, dv equal to the link cost uv. If there is no direct connection between v and u, we will set dv as infinity. And for the second part, it's a loop part. We will find the w or whatever router not in n prime such that dw is a minimum. Then we add w to n prime, and then we update dv for all v adjacent to w and not in n prime. Then we need to update this dv based on this minimum minimum equation, actually based on these two values, this one and this one. We need to do a compare to see which value is smaller. Then we just update the smaller to this dv. So the physical meaning for this equation is a new cost to v is either old cost, which is this dv, or known shortest path cost to w plus cost from w to v, which is dw plus this cwv. So however, if you don't understand this loop part, it doesn't matter because later we have an example. I will show you guys to understand this loop part. Then let's see this example. So initially we only add u, which is a source router, into the n prime set. Then from u, we will check all other nodes to see the path cost from all other node to u, which is a d v w x y and z. And also we will check the p v w x y and z, which is a preprocessor from u to that router, the predecessor for the link for the path from u to that router. Then first let's see from u to v to the first one, we have a direct link with a cost 7, and from u to w with cost 3, from u to x with cost 5. However, from u to y and to z, there is no direct link. Therefore, we will set the cost equal to infinity, just like that. And for this part, actually, it's just the initialization step, which is the first step we need to do for this algorithm. Then, among these values, we need to pick up the minimum value, which is 3 with u, because here you can see find w not in n prime such that dw is a minimum, just like the example show us the 3 is the minimum among all other values. Then we need to add w to n prime. So what's the w? This one is the w here. But in the pseudocode, the w actually just represent a variable. Then we can add w into the n prime. So you can see here, in the n prime, in this set, we have two routers, U and W. Then our next step is update DV for all V adjacent to W and not in n prime. And based on this equation, we will do the update. Then let's see the example how it works. So since we just add W into the set n prime, then we need to check the adjacent neighbors or direct neighbors to W, or all other, I cannot say neighbors, I can say all other routers which is not in n prime. So we need to check them one by one to see if we can find a shorter or least cost path from U through W router to another router. So first, let's see from U through W to V. For this path, the cost will be 3 plus 3. This link, this UW plus WV will be equal to 6W. Since the old value 7 is greater than the new value 6, then we can replace the old value with a 6 for the path from U to V. Then let's keep checking to X, which is the path from U, W to X. So the path for this path, the cost will be 3 plus 4 equal to 7. And for the O, the cost from U directly to X is equal to 5. So the 5 is smaller than 7, then we just keep the old value. Then let's see from U to Y through W. The cost equal to 3 plus 8 equal to 11. And the preprocessor will be W. And for this one, since the old value is infinity, therefore we can update it with 11W here. And for router Z, since from W to Z there's no direct link, therefore the path cost is still infinity. And among the 6W, 5U, 11U, and infinity, the smallest or the minimum number is 5. Therefore, we can add x into n prime. Then inside the n prime, we have U, W, and x. So we only need to check V, Y, and Z with x. Then let's see. If from U to Y through X will be UXY, the path cost will be 5 plus 7 equal to 12. However, 12 is greater than 11, greater than this 11 value. Therefore, we will keep this, I'm sorry, I mean for this one, because this one is the old value. This is a new value. Therefore, for this updated value will be 11W as well. And for node Z from X, we can find a path which is UXZ. And for the path cost will be 5 plus 9 equal to 14. So compared to the previous or old value infinity, so we can update the DZ with 14x. And for node V, since from X there's no direct path from X to V, so we just keep the old value 6W and put it here. And among these three values, 6W is the smallest one. Therefore, we just put V into set n prime. Then we keep searching. Use the same strategy. So since inside the n prime set we have u, w, x, and v, so we only need to check y and z, these two routers with v. And from v to y, then the path um, from u through v to y will be u, w, v, and y. So the total cost will be 3 plus 3 plus 4 equal to 10. And we compare with the old cost, which is 11. So the current cost is smaller. Then we will replace it with 10V. And for node Z, um, from V, there's no direct path from V to Z. So we will keep the old value, which is 14x. And between 10V and 14x, 10 will be smaller than 14. Then we can add y into our n prime set. So currently we only have one left, which is the dz, which is router z. So we only need to check the least cost from y to z. So previously the old value is 14. Then currently, if go through y to z, the cost will be 12 because the path is from u, w, v, y, and z. So the cost will be equal to 3 plus 3 plus 4 plus 2 equal to z, which is this path. Therefore, finally, we can add z into the n prime set. So here there's a note. Construct shortest path tree by tracing predecessor's nodes. So, which means if you want to find a path from each from any other routers back to the source, you can tracing the predecessor nodes. For example, if we want to find the path from U to Z, first you will see Z, which is this one, 12Y, and then the predecessors is Y. Then we will go here. And when we around Y, we see the predecessors is V. Then we go here. We see for the predecessors for V is W. Then we go here. And finally we reach U. So the path will be Z, Y, V, W, and U. And for any other routers, you can use the same strategy to find the path from that router back to the source router. If there's a tie can exist, so we can broken the tie arbitrarily. We just randomly pick up a router and to do the calculating. In order to reinforce our understanding of this algorithm, so let's do another example. So initially, still we only have a source router in the n-prime set, which is router U. Then for the router U, we need to do the initialization step, which we check all other routers to see the path cost to U. And from U to V, we can see is 2. and also the preprocessor is u. From u to x is 1, and from u to w is 5, and from u to y there's no direct path, therefore which is infinity. And the same thing for router z. Then among these values 2u, 5u, 1u, infinity and infinity, this one is the minimum value. Then we add x into set n prime. Then we have a ux in the n prime. And then we check all other routers which is not in n prime to router x. Then start from router x, we will check them one by one. First, let's see xv. So the path will be from u through x to v. The path cost will be 1 plus 2 equal to 3. However, the old path cost is only 2. Therefore, we will keep the old value. And from x to w, which is the path is uxw, the path cost will be 1 plus 3 equal to 4, which is better or smaller than the old value. Then we can do an update with a 4x. And for router y, the path will be uxy. The cost will be 1 plus 1 equal to 2. Then we do an update here. And for z, there's no direct path between x and z, so we keep the infinity. And between 2u, 4x, and 2x, these are three values. We have a tie here, 2u and 2x, because both of the router v and the router y, they back to the source router, the path cost is equal to 2. Then we just randomly pick up 1. So here we just pick up router y and put router y into the n prime set. Then we further check the routers which is not in n prime set, compare with y. Then we can see from y to w, the path will be u, x, y, w, which is equal to 3. So compare with the old value 4x, so we can do an update with a 3y. And for router z, we can have a path uxyz, so the cost will be 4y. Then we can do another update here. And also based on these three values, 2, 3, and 4, we will add a v into our n prime set. Then we keep checking. We will check w and z to v. So from v to w, the cost is u v w, which is equal to 5. So 5 is greater than the old value 3y. Therefore, we just keep the old value 3y here. And for router z, still keep the same, because from v there's no direct link from v to z. Then we just keep the old value here, update here. And finally, not finally, here we have a comparison between 3 and 4. Then we need to add w into our n prime set. Then we only need to check w with z, and we can find we still need to keep the old value, which is 4y. And then finally, we can add router Z into this set. Then we finished. So after we finish this update, we can get this shortest path tree from U. It looks like this. And then we can also insert the forwarding table into U router. And the forwarding table will be looks like this. So if you find any, if router U receive datagram destinated to any routers here, so we can tell which link should take. For example, if the datagram destinated to router Y, it will take UX, this link, because Y is here. This is the shortest path from U to Y.